Welcome back to the deep dive. Today, we're going deep, really deep, into the plumbing of the internet.
We are. We're looking at a piece of tech that is so fundamental to, well, everything you do online, but it's completely invisible.
It really is. So, I want you to picture a scenario. This happens billions of times a day.
All right.
You're at your desk in London, you've got a friend online in Los Angeles, and maybe a colleague working in Shanghai.
Right. All over the world.
Exactly. And all three of you, at the same time, you access the exact same IP address. Let's use the famous one, 8.8.8.8.
Google's public DNS. Yeah.
And magically, you all connect instantly.
Right.
You get the right response, super fast. But here's the trick.
Hmm.
None of you actually connected to the same physical server. You each hit a different identical clone, one that was perfectly placed for you.
And that's not digital magic. That is Anycast routing. It's really the key ingredient that makes the modern internet both fast and incredibly resilient.
So if the old way, Unicast, was yesterday's internet.
Right, rigid and limited by geography, then Anycast is the solution that really allows for global scale.
Okay, so that's our mission for this deep dive then. Let's unpack the genius behind Anycast.
Yeah, we want to understand the mechanisms that make it possible to share one IP address all over the world and really get into the four brilliant advantages that make it a cornerstone of the internet.
All right, let's do it. To really get at Anycast, I think we first have to talk about the old standard, right? Unicast. What was the big problem with that model?
Unicast is all about uniqueness. Think of it like a street address on a letter.
Okay.
If you send a package to 742 Evergreen Terrace, there's only one house in the world with that specific address.
So in network terms, every single server had one unique IP address that pointed to one specific physical box in one data center somewhere.
Exactly. And, for years that worked fine. But when the internet went truly global, that rigidity became a huge problem.
How so?
Well, imagine one server in Frankfurt trying to serve users in Cape Town and Seattle.
The data has to travel vastly different distances.
Right. You get massive delays, what we call latency, just because of physics. Data can only move so fast.
And I'm guessing there's a bigger problem too.
A much bigger one. It creates a single point of failure. If the power goes out in that Frankfurt data center or a network cable gets cut,
everyone connected to that address is just offline.
Instantly cut off. It's fragile. It just cannot scale to billions of people who expect instant service.
So Unicast is location dependent, which means delays and these single points of failure. Anycast just flips that whole idea around.
Completely. That's why I love your term for it, the clone army solution.
It seems to fit.
It's perfect. Anycast basically says, we don't care about a unique location, we care about availability and speed.
So the idea is you have multiple physical servers, maybe in Amsterdam, Sydney, Sao Paulo.
All over the world, and they all advertise and share the exact same IP address at the same time.
Okay, wait. That still sounds like it should cause chaos. How does a router know which server is the real 8.8.8.8 if like 30 of them are all shouting, I am at once?
This is where the classic pizza delivery analogy comes in.
Oh, okay.
When you call a big pizza chain's national 1-800 number, you're dialing one number, right?
Right.
You don't care which store in your city answers. You just want the one that's closest and can get you a pizza the fastest.
So Anycast is like that automated dispatcher.
Exactly. The network's job isn't to find the one unique home for that IP. It's to find the nearest functional clone.
Okay, that makes the goal super clear. But how does the network, the actual routers and cables, make that call? How does it calculate the nearest neighbor? That seems really complex.
It is, and it requires a very smart decision maker. And that brings us to the protocol that makes it all work.
Which is?
The Border Gateway Protocol, or BGP. It's often called the Internet's global navigation system. It's always updating, always aware of what the network looks like.
So when I try to connect to an Anycast IP, my request goes out and eventually hits the BGP system. What does BGP do when it sees, say, 50 different servers, all claiming to be the same address?
This is where it gets really clever, because it's not just about simple distance, like miles on a map. BGP is measuring network efficiency. You see, the internet is really a network of networks. Each piece is owned by a different company, an ISP, a university, and these are called autonomous systems, or ACEs. When BGP sees your request, it looks at all the possible paths to get to one of those clones. And the most important thing it looks for is the AS path length.
A is path length. What does that mean?
It wants the path that crosses the fewest of those network boundaries, the fewest AS hops.
So it's not about physical distance, it's about the number of handoffs between different providers.
Exactly right. Think of it like a relay race. A path that only passes through, say, 3 different networks is almost always seen as better than one that passes through 7.
Even if that 7-hop path looks shorter on a map.
Even then, fewer hops usually means a more stable, faster route with less congestion.
That's a huge insight. So the shortest route isn't a straight line. But hang on. If I'm in London, wouldn't a server in Paris be physically closer than one in Amsterdam? How does the network choose if BGP is just counting those hops?
That's a great question, and it shows the next layer of complexity. BGP gives the main preferred route based on that path length, but local routers can add other data,
Like what?
like actual latency measurements. So if the router in London knows the path to Paris is super congested, but the path to Amsterdam is clear.
It'll choose Amsterdam, even if it's a few more miles away.
Precisely. The end result is that the user in London is routed to the closest, most stable, and most efficient server available at that exact moment.
So all that complexity is hidden in the network itself. For the user, it just works.
It's seamless.
And this leads us right into the 4 huge advantages of Anycast. Let's start with the obvious one, lightning fast speed.
Right.
We've kind of covered it, but it's just physics, right?
Mhm.
Connecting a user in Sao Paulo to a server in Brazil instead of California means the data travels less distance.
And that reduced travel time, that lower latency, is what makes everything feel so snappy and responsive.
Yeah, but just as important is the second advantage, prime network resilience,
This is a huge one. Unicast had that single point of failure we talked about.
which was terrifying.
Anycast completely solves it because you have all these clones advertising the same IP. If one server dies, hardware fails, a fiber line gets cut by a backhoe.
Which happens.
Oh, it happens all the time. BGP just notices that route is gone. It removes that path from its map, and traffic instantly and automatically gets rerouted to the next closest healthy clone.
And this all happens in milliseconds with no human needing to do anything. The network just heals itself.
It's the ultimate automated failover system. And that self-healing power brings us to the third advantage, which is so important today, DDoS defense.
Distributed denial of service attacks.
Yep. The goal of a DDoS attack is to flood a single target with so much junk traffic that it gets overwhelmed and goes offline.
With a unicast server, that's pretty easy to do.
It is. But when attackers aim at an anycasted IP address, something brilliant happens.
The traffic doesn't all go to one place.
Exactly. That massive flood of malicious traffic gets distributed by BGP across dozens or even hundreds of servers all over the world.
So the attack gets diluted.
It gets completely diluted. Instead of one server trying to handle 100 gigabits of attack traffic, you might have 100 servers each handling just 1 gigabit. It's a divide and conquer defense that's built right into the architecture.
The attack traffic basically load balances itself across the globe. That's incredible. And the fourth advantage is more subtle.
It is. It's about operational simplicity.
For the user, it's simple because you only ever need to remember one address, like 8.8.8.8.
Right. And for the operator, it's also simple. They can set up a new server in a new city, let's say Lagos, give it that same Anycast IP.
And BGP just automatically starts sending local traffic there.
It allows for incredibly fast and easy scaling across the world with one consistent setup.
So this isn't just some, abstract theory. This is the engine running huge parts of the internet right now. Where do we all use this today?
Absolutely. The biggest examples are the ones we mentioned, Google's 8.8.8.8 and Cloudflare's 1.1.1.1.
When you put those in your DNS settings.
You are not hitting a single computer in California. You're hitting the closest of hundreds of their data centers. It's the only way they can handle trillions of DNS requests a day without just collapsing.
And DNS itself, the internet's phone book, it has to be built on this.
It is. This is probably the most critical use. Everyone's heard there are only 13 root server addresses for the whole internet.
Right.
But if there were really only 13 physical computers answering those, the internet would have broken decades ago. Those 13 addresses are actually run by thousands of physical servers spread all over the world using Anycast. Without it, the internet just couldn't work at this scale.
And this is also why my Netflix stream doesn't buffer.
Absolutely. Content delivery networks, CDNs from companies like Akamai, Fastly, Cloudflare, they all use Anycast. When you stream a show, Anycast makes sure you're pulling that huge video file from a server clone that's as close to you as possible.
Low lag, instant loading, whether I'm in Taipei or Tucson.
Exactly. And it's the same for online gaming. It's essential for getting millions of players to the right regional server for a smooth experience.
So gamers, that's why you get connected to the US East server automatically. Anycast just sent you there.
Yep.
Okay, we've covered the brilliance, the speed, the resilience, but it's not a silver bullet. There has to be a catch. a place where Anycast is actually a bad idea.
There is a critical limitation, and it all comes down to a concept called state.
State.
Anycast is brilliant for stateless services. That's any transaction where each request is totally independent of the last one.
Like a DNS lookup.
A DNS lookup is a perfect example. You ask, what's the IP for google.com? The server answers. The conversation's over. The server doesn't need to remember anything about you. If your next request goes to a different clone, who cares?
Right, it doesn't matter. But where does it break?
It breaks for stateful connections. Stateful means the server has to remember and track what's happening in an ongoing connection. Think about a session ID or where you are in a large file download.
Okay, give me a concrete example of that.
An encrypted banking session or a big file upload. These use a protocol called TCP, which needs continuity. When you start that connection, the server creates a session and starts tracking your progress.
I'm with you.
Now, imagine if, mid-upload, your traffic suddenly gets rerouted to a different physical server that's also using that same IP.
Oh, that new server has no idea who I am or what I was doing.
None at all. It's like your bank teller vanishes mid-transaction and a new one appears and says, "Can I help you?"
The state is lost. You have to start all over.
Precisely. The connection just breaks. That's why Anycast is amazing for the initial connection, to get you to the closest data center. But often, for the actual long conversation, the system will switch you to a normal, unique unicast IP at that location.
So Anycast gets you to the right neighborhood, but Unicast takes you to the specific house for the actual meeting.
That's a perfect way to put it.
Okay, so if we pull this all together, Anycast is this powerful, invisible technology. It's the ultimate work smarter, not harder solution for the internet, using smart navigation to beat geography.
It really is. And you have definitely used it dozens of times today. Every time you loaded a big website, every time your computer looked up a domain, every time some network failure happened somewhere and you didn't even notice.
It's what keeps services online even when bits of the internet are physically broken.
And that prevents small, local problems from becoming huge global outages.
Knowing this is genuinely empowering. So next time you see a headline about a data center fire or a submarine cable getting cut,
You can remember that there are these massive, hidden, automated systems like BGP and Anycast working to contain the damage and keep things running.
you now know the secret reason the internet stays fast and resilient for billions of people. It's a true network wizard's insight.
Indeed. And it makes you wonder, right? If the entire internet relies so heavily on this one protocol, BGP, to route everything to these crucial Anycast systems, what other invisible plumbing is holding things together right now just to keep your connection stable? How centralized is the brain for this globally distributed clone army, and what happens if that brain starts giving out bad directions?
That is definitely something to think about the next time you hit a single IP and get an answer from a clone army thousands of miles away.